Welcome to my presentation. Today I'm going to present my the topic of interest, a comparative study and implementation of brain tumor detection from magnetic resonance imaging (MRI) using deep learning algorithms. I am Orko Shaha, and let's get into the presentation now. So this coursework will mostly cover these sections: interaction, objective, literature review, methodology, implementation, result, discussion, future scopes, challenges, and limitations. I'm gonna briefly go through all the sections in the next few minutes. Medical imaging technology and artificial intelligence have transformed the way diseases are diagnosed and predicted. Um, so, but the human brain, which is enclosed by a bony skull, is a major decision-making component of the human anatomy. A brain tumor is a collection of atypical cells that forms in the brain. Any development in the region will lead to major issues. Brain tumors constitute some of the most lethal types of the tumors of the world. Uh, mm, there are over 12,000 new cases of brain tumors each year, and over 5,400 deaths from brain tumors in the UK itself. Unfortunately, the prevention rate in the UK is only 3%. And uh, in the past, machine learning models and deep learning models actually showed very satisfactory results with fewer training samples and a shorter training period, which are actually few of the constraints when working with medical data processing, because there are very few um, data available. So the objective of this coursework is to develop an accurate and reliable system for detecting brain tumors from MRI images using deep learning algorithms, evaluate the performance of different deep learning architectures, explore the use of transfer learning, where pre-trained models are fine-tuned, and the efficiency of the training process, validation process, and the accuracy of the model. Um, and finally, validating the deep learning models on a large and diverse data set, and compare the performance with the state of the art methods in the field of brain tumor detection. And as an extension of the coursework, I implemented. um, uh, I deployed the model to a live website using Flask framework in Python programming language. The applications can of this project is huge. The early detection and diagnosis of brain tumors, the reduced reliance on invasive diagnostic procedures such as biopsy, automation in the brain tumor detection process, which is supposed to end up reducing the number of reducing the workload of the radiologists and clinicians, and potentially improve the patient outcomes as well. The integration with other medical imaging technologies such as PET or CT scans to provide a comprehensive view of the patient's condition, um, and improved accuracy and efficiency of brain tumor detection, as deep learning applications can be trained to recognize subtle differences in MRI images that may be difficult for human experts to detect. The advantages are yeah, DL can automatically learn complex features from MRI images without requiring manual interception. DL models can be trained on large data sets. It can be used for both tumor detection and segmentation, enabling both better visualization of tumor boundaries and localization. And it can provide a faster and more accurate diagnosis. As I was saying, challenges are lack of annotated data available, variability in imaging protocols, overfitting is always a big concern, yeah, in this kind of um, the projects, and interpreting the decisions made by humans can be made by the DL models can be challenging, and there is a risk of creating black box models that are difficult to explain. And the limitations can be that the models can be affected by size, location, types of tumor, as in the data set in a whole. These models require a large amount of data, which means it is very data hungry, and can be difficult to obtain for rare or uncommon tumor types. These models may not be able to capture all the relevant features for accurate brain tumor detection, and there may be additional factors such as patient history and other clinical data that could improve the accuracy of the diagnosis. So I for this project, I actually used a dataset that is publicly available on Kaggle, put together by Masood Nikpurver, which is and this dataset is a combination of these three dataset: Figshare, CERTAS, and BR35H. This data set contains 7,022 images in total. That is already pre-classified into four classes of tumor types: glioma, meningioma, pituitary, and another one is no tumor. And all these images are in sagittal, axial, and cornal planes. So here is distribution of the data set. As you can see here, the data set is pretty much balanced. Now let's get into the methodology, how we completed this project. So the in the input image, we um, input the images from the dataset that we just discussed, and after that we moved on to the pre-processing. In the pre-processing step, we did the resizing, labeling, data augmentation, and data generation. By preceding this step, there is a deep learning models of where we trained the model, tested the models, then evaluated its performance, and finally showed the prediction. And after a vigorous training process, we leveraged Flask framework in Python programming language and locally hosted the website to show its output. In the pre-processing, we considered these parameters: base size to be 12. For this, the one epoch of the data set was considered because of the resource intensiveness, and the machine constraints. The image size was resized to 128 times 128 before processing further. Um, the brightness was chosen between 0.8 to 1.2, and same goes for the contrast as well. Um, Moving on to the visualization, here is an image. We grayscaled it first, and then in this part, it shows the histogram of the image pixel values, as well as the cumulative distribution function. And after that, we implemented a binary mask using a threshold value of 60, and it gave us this beautiful image. From this, you can actually see the location of the abnormal growth in the brain, which can be interpreted as a potential tumor. uh, and then we move on to the training the model phase. Uh, so before we move on to the training phase, I want to show some of the code that I've written for this particular. Um, this is the overview of the GitHub link that I have provided. In the README, I put some of the important information before proceeding them to run this code. And then for the visualization part, we implemented a few steps in this part. We imported all the necessary um, um, libraries, and this whole thing is actually was built using Google Colab Laboratory. The code is written that way. In this part, the data set is actually divided into training set and testing set. We further assigned it to training percent, train levels, then showed the pie chart of the train levels, so which shows us this. And after that, we implemented a bar plot to show the actual number of each of the um, um, folders that contains the different types of tumors. uh, and after that, we implemented this code uh, to show the uh, training and testing data percentage in a pie chart. Following which, as I was saying, we grayscaled the image first, and then we leveraged the SciPy's ND image module and created a histogram and a cumulative distribution function for this particular image. Just changing the name of the image here would end up with a different sets of set of image, and it will show a different histogram as well. It is already tested and um, uh, ready to run. And for this one, we implemented a binary mask on top, and set the threshold value to 60. This shows us this. And finally, we smoothen the intensity value, select the high intensity pixel to identify the possibly infected region where the abnormal growth of the brain cells can be, and this shows us this. And we also implemented in a different way as well. Now, moving on to the training phase. So for this, we actually implemented three different models. One of them is ensemble model, where we actually stacked three of the similar structured the models on top of each other, and finally averaged the performance of them uh, to use it in the prediction stage. So this is the overview of the model. Uh, following this, we actually cross validated the model using k-fold cross validation, and this is the overview of the model. In the VGG16 pretend model, we implemented this approach, which I am going to show you a little later. And finally, we used another pretend model, ResNet 50, and the overview is here. And based on the performance, where we found out that VG16 works the best in terms of the prediction performance, and the ResNet is a close second. And finally, these are the model training plots from VGG16 and ResNet. That's because these two actually work the best. And finally, this is the confusion matrix of the prediction result. And this is the classification report for both of these pretend models. And this is the prediction uh, uh, performance from the model. As you can see that we use the VGG16 model to predict a particular class, and this image is actually no tumor, and it says 100% conclusion it's a no tumor, which actually concludes our uh, uh, prediction. However, we moved on to the deployment part, where, as I said before, we used the Flask framework and used a pretty minimalistic website to make sure that this project is very focused and minimal, um, to further use. Um, in this deployment part, all we need to do is upload an image. The image will be immediately resized to 128 times 128, and then after the pre-processing, it will generate a prediction, and finally retrieve the highest predicted probability, and show the prediction. Uh, Now let's move on to the code here. So in this particular code, this part is pretty much similar. We created the train paths and train levels, test paths and test levels for further use, and use the shuffle function to make sure it doesn't change every time we run it. Then we um, split the whole data set into training set and testing set. We use the test size as 0.2 and set the random state to 42. Then we normalized the split data set, and then leveraged one hot encoder. Uh, Now we're gonna get into the model design. So in this part, these there are three different models that we implemented. This is the whole um, a model structure that we built here in the a sequential model. We implemented flatten, dense, and finally the output layer using softmax activation function. For the evaluation, we yeah, so for the compilation, we use the Adam the optimizer, categorical cross interface loss, and categorical accuracy in the compilation. Finally, we get into the ensemble model, where we used three models. Here you can see all of them, and then we stacked all of them together. Then used the predict on batch the function to create a prediction. You can see the accuracy here is 0.923, which is a 92.3%, and the loss is 0.3048% here. Then we use the model in the k-fold cross validation, and we found out the loss is 0.38378%, and the accuracy is 0.9291%. Using VGG16 pretend model, we actually implemented a different approach. We first did the data augmentation and data generation, um, uh, where we um, chose to work with brightness with 0.8 between 0.8 to 1.2, and contrast between 0.8 to 1.2. We reshaped the image, and then moved on to the data generation. Here you can see the function that generates the batches of data for training. Then we moved to the VGG model, which is here. We also implemented some dropouts to possibly try to make sure of the performance being a little better. In this one, we again used Adam sparse categorical cross entropy loss and sparse categorical accuracy um, the metric, and this is the output. You can see that the accuracy is 0.9718%, and the loss is 0.08%. And finally, using ResNet 50 pretend model, we got 0.96% and 0.10%. In this um, um, in this code, I actually try to illustrate how I started working on the data, and how I ended up in this one. So this is definitely a draft one. I am not supposed to share this, but well, for understanding the project a little better, this can actually come in a little handy. So this is why I put this here. So in this part, you can see this part of the um, this part of the project where I tested the performance prior to the prior to deployment. So here I uploaded an image, yeah, implemented the um, model, and finally got an output. It says that 97.28% conclusion that it does have a tumor. So you can see from the image here that there is a tumor here actually. Similarly, I did the same thing for each of them, and got a result. Now we move on to the uh, main part where we implemented, well, we deployed the model. As you can see here, it is pretty minimalistic. Where all we need to do is choose an image from your data set, and you can choose any of it and press. It says prediction tumor, which means that it is already it already says that it has a tumor in it. So this is the overall code here. So in this one, we leverage the OpenCV library as well. We loaded the model that we saved here. This part says that um, uh, for glioma, it will say tumor. For the meningioma or pituitary, it will also say tumor. And for uh, another one that has no tumor in the MRI scan, it will say no tumor. And just in case it fails to um, implement or fails to predict a particular image due to its limitations, it will say unknown. And this is the overall code that I wrote here. So here I am initialized the email, uploaded the image file, initialized the name, and saved it in a path which is this one. If you go in this, it will save all the images that you upload here. And then we move on to the prediction phase, and then classification. So this is the overall index.html file where I am used the bootstrap framework as well. And this part of the code actually will show the prediction here that is generated. The future scope of the project is experimenting with various classifiers, voting techniques, discretization techniques, and different networks and topologies. Experimenting with other deep learning algorithms, um, finding greater resources, and yeah, improving the data accumulation techniques, taking additional rules like associated rule mining and other clustering techniques into account as well. And new feature selection approaches may also be devised. Thank you.